like in our study of proportions, we're going to find the confidence interval for a population mean. And it still has that same structure where you take the statistic, you add or subtract the critical value times the standard error of the statistic. Now, in our study of proportions, this critical value was always z, but here in just a moment, we're going to learn where when we're dealing with population means, we're typically going to have to use the t-distribution. So first, let's look at example 12.6 because this is the only case where you can use that z-distribution. In example 12.6, we read that cosmic radiation levels rise with increasing altitude, prompting researchers to consider how pilots and flight crews are affected by increased exposure to cosmic radiation. The CDC estimates a mean annual radiation exposure of 3.07 millisievert per year. I need to look up how to pronounce that. Suppose that this is based on a simple random sample of 100 flight crew members. So here, what is mu? It is the mean annual radiation exposure of all pilots and flight crews per year. Doesn't apply to people who stay on the surface of the earth most of the time. And so we only know the sample mean. The CDC estimated a sample mean based on a simple random sample of 100. So if we wanted to find a 95% confidence interval, we would take our statistic, which is 3.07, we would add and subtract that 1.96, our z-star value, and then our sampling distribution, standard deviation, would be 0.35 divided by the square root of 100. Now we're going to go to StatCrunch to get this answer. So here we're going to go to stat, z-stat, one sample with summary. And this will be probably the only time we use the z-stats for the rest of this class. Here we have our sample mean was 3.07, the standard deviation was 3.5, 0.35, there we go, and the standard or sample size was 100. So I just took the information from the problem, and if I click on confidence interval and we want a 95%, it's going to give me my confidence interval. Let me just slide it over so y'all can see. Here we go. We have our lower limit and our upper limit, and so we are confident that the true value of the mean is somewhere between 3.001 and 3.139. Sometimes I write those in intervals, and sometimes I like to show where mu has to be between those two values, and so sometimes I actually prefer writing it as an inequality. Now, if you were paying attention, you were given the population standard deviation sigma. If you knew the population standard deviation, then you would have to know the population mean. Okay, there's no way to know the population standard deviation without knowing the population mean. And if you know the population mean, you don't need to do a confidence interval. You can just state it. You do a confidence interval because you don't know mu. And if you don't know mu, how in the world would you know sigma? So this particular confidence interval where we used z really is only a practice in theory because you'll hardly ever know sigma without knowing mu, making a confidence interval pointless. So what do we do instead? We use what's called the t-distribution. And the t-distribution really isn't that different from, and before I talk about the t-distribution, proportions can use the z-distribution. Proportions always go to normal. I don't need to go into that. If you really want to study, you can look online. But proportions, normal distribution's fine. For means, we can't do that without knowing sigma. And it mostly has to do with the fact that P is an unbiased estimator, or P hat is an unbiased estimator for P, but S, the sample standard deviation, is not unbiased for sigma. And so since it's not unbiased, you can't use this Z distribution. But anyway, that's for a third or fourth course in statistics. Right now, we just recognize if we don't know sigma, which we won't know sigma, we need to use this T distribution. And we do want to understand a few characteristics of this T distribution. It always will have a particular degrees of freedom, and we'll talk about that, what those are just here in a second. But no matter how many degrees of freedom, this distribution will always be bell-shaped, and it will still be centered around 0, just like our standard normal distribution. Now, every T distribution has greater variability than the normal distribution. As the sample size or the degrees of freedom gets larger, it becomes closer to the standard normal distribution, but it always is slightly more variable, which means it spreads out just a little bit more than the regular standard normal distribution. But as the number of degrees of freedom increases, the variability will decrease. And as the number of degrees of freedom increases, the corresponding sequence of T distribution approaches that standard normal distribution. And you can see in this graphic that there's 3 lines. The Z curve is the darkest one here, and the T curve with 4 degrees of freedom is the lowest one. And you can see that it is higher out here in the tails. It's a little more variable. The degrees of freedom of 12 gets a little bit closer to the Z curve. Once you get to about 100 or so degrees of freedom, there's a very, very slight difference between these two curves. So, what are these degrees of freedom? You don't really need to know all about the degrees of freedom, but what you have to know is you find the degrees of freedom by doing the sample size minus 1. Part of why that is the case, because I said that that's S, the standard deviation of the sample, is not an unbiased estimator, that it is biased when estimating sigma. That adjustment that needs to be made, if you will, requires us to have this n-1 degrees of freedom. So if you're really interested in where that's coming from and you have lots of free time, you can search degrees of freedom in your Wikipedia or Google. But for the sake of time and the scope of this course, you need to know that it's n-1 and it has to deal with the estimations that we're doing. So if we can't use the normal distribution and we use this T distribution instead, there is a T-table, and it's in the back of your textbook, and it's not that hard to read, but since we're using StatCrunch for this course, we're just going to use StatCrunch, but we need to recognize that we go to our T distribution. There are a few requirements, though, before we can use the T distribution, and the first one is typical. We need to have either a simple random sample or a representative sample. And then here's the next one. This one's a little unique. Either your sample size has to be large, 30, remember 30 is that central limit theorem that says that our sampling distribution will be normal, or we have to know that the population distribution is approximately normal. So the original distribution either needs to be normal or our sample size has to be big enough that the central limit theorem kicks in so that we know that the sampling distribution is normally distributed. Even though we're not using the normal distribution in our calculations, that T distribution is related in such a way that we need to have that condition met. But as long as those two conditions are met, then we can go ahead and use our critical values of T that are programmed into the computer. The degrees of freedom is actually also programmed into the computer, and we'll calculate our confidence interval just like we always had. The interpretation is the same. It's just about mu this time. So we can be confident that the value of the true population mean this time is included in that calculated interval. So you would always want to put that somehow in context. And then the confidence level, just like before, is giving us the long run proportion of the time that our method is expected to be successful. Remember, we usually just take one shot at this. It may work, it may not, we don't know. But our method in repeated sampling would work whatever percent of the time. So let's see how we would do this. In example 12.7, we're looking at the drive-through model that we talked about in the introduction, and patients were evaluated while they remain in their cars. So they had 38 people that were given those scenarios, and in this case, the sample mean was 26 minutes with a 1.57 standard deviation. So let's estimate the mean processing time for the population. So we do a confidence interval. We need to do a t-interval because we only know the sample standard deviation. So we go to StatCrunch, and it's t-stats. So from now on, go to t-stat because I don't think any problems in this course other than that one example are Z. Go to summary. We have our sample mean of 26, our standard deviation 1.57, and our sample size of 38. We want a 95% confidence interval. We click compute, and our lower limit is 25.48 to 26.52. And so we're confident that the true mean is between 25.48 and 26.52 minutes. Now we could use that information to compare to what it would be in the emergency room to see if this is an effective way to decrease the processing time for flu patients. We have two more examples that we're going to do real quick. Example 12.8 is looking at the mean time that patients who broke a hip had to wait for surgery. We had a sample of 204 people. The sample mean was 28.5 hours, and the standard deviation was 16.8 hours, and we wanted a 90% confidence interval. So go to t-stat with summary. Now we're going to go to with data here in just a minute. So our sample mean, we type that in. Standard deviation, we type that in. And our sample mean is 204. We go to our confidence level, and we change that to 0.90. And our confidence interval, the mean time is between 26.56 hours and 30.44 hours. Now in example 12.9, we actually have some data. And so I'm going to type that in. We have 23, 22, 21, 24, 19, 20, and 20. It's typing too fast. And what this data represents is a really interesting study that if you read about the background of the study in the textbook, I highly recommend it. It's really interesting. But it was looking to see if chimpanzees would dispense food for themselves or for a chimpanzee in another cage. So what they were looking at is how many out of 36 trials that each of these 7 chimps chose to give food to both chimps. And so we're looking to see, they know that they can give food to the other chimpanzee. How often do they do it? And you can see that it really wasn't that much out of those 36, which is why the study was chimpanzees aren't charitable. But here, to do this calculation, we go to t-stat, one sample, but this time we have with data because we have the raw data. And so we'll click the variable 1, I didn't name it. We go to confidence interval, and we do want a 99% confidence interval here. And that's all you have to change. You don't have to worry about anything else. Click compute, and we get our result, that the mean number of times that the chimpanzees for the population would choose this is 18.76 and 23.81. So just a little bit more than half of the time these chimpanzees are choosing to feed both chimps. So that's how you use StatCrunch to calculate these intervals. We're always using the t-distribution because we don't know sigma, and so we have to estimate a little bit using the t-distribution, but the calculations and the interpretations are exactly the same as we had for proportions.